All right, today we're putting on our detective hats to solve a classic mystery from the world of computer science. We're going to crack the case of how databases can possibly handle millions of things happening at once, all without losing or scrambling your data. Let's dive right in. So think about this. You're transferring money. At the exact same time, your paycheck gets direct deposited. How on earth does the database make sure both of those things happen correctly and your final balance is what it should be? This is the core problem of what we call concurrency, and honestly, it's what keeps our entire digital world from just falling apart.
And this, right here, is our crime scene. If a database isn't super careful, letting multiple operations run wild can corrupt data, leaving it in what's called an inconsistent state. That's really just a fancy way of saying your bank balance could be totally wrong, or an online store thinks it has stuff to sell that, well, it already sold. It's a huge deal.
But don't you worry, we've got a game plan to solve this whole thing. First, we'll get a closer look at the problem itself. Then we'll bring in the hero of our story, serialization. After that, we'll learn how to find the clues, the conflicts, build a visual map of those clues, and then finally, we'll deliver the verdict and see what the big payoff is.
So, how do we actually guarantee that our data stays consistent? The answer is this really powerful idea called serialization. You should think of it as the absolute gold standard for database safety. It's the one rule that ensures a database always stays correct and predictable. Now, the simplest way to keep things safe is just to run everything one at a time. This is called a serial schedule. Just picture a single file line. Transaction A goes from start to finish. Then, and only then, transaction B gets to start. It's completely foolproof, always gives you the right answer, but, and this is a big but, it's incredibly slow. And this is where the real magic comes in. A serializable schedule lets us run things all mixed up together, getting all that speed from doing things at once, but, and this is the key, it guarantees that the final result is exactly the same as if we had run them one by one. So we get the performance of running things in parallel with the total safety of running them in a line. That's our goal.
Okay, that sounds great, but how do we know if one of these jumbled up schedules is actually safe? We need a test, right? We need a detective's tool for finding clues, and in the database world, those clues are called conflicts. For two operations to be a conflict, they have to check three specific boxes. First, they have to come from different transactions. Makes sense. Second, they have to be messing with the exact same piece of data, like the same row in a table. And third, and this is the most important part, at least one of them has to be a write, an operation that actually changes the data. This little table here just makes it crystal clear. You see, two transactions can read the same piece of data all day long, no problem at all. The trouble starts the moment a write shows up to the party. A write bumping into a read or a write bumping into another write on the same data. That is the clue we are hunting for. Okay, so we know what a conflict looks like. Now it's time to actually start our investigation. We're going to take a schedule of operations and we're going to build what's called a conflict graph, which is basically our visual map of all the clues we find. So here it is. This is our case file. We've got three transactions, T1, T2, and T3, and this whole timeline of 10 operations all jumbled together. It looks pretty complicated, I know, but our conflict rules are going to help us make sense of it all. Let's start the hunt. And we've got our first clue. Look here. At time T3, transaction T3 reads the data item X. Then, way down at time T9, transaction T1 writes to that same data item X. That's a classic read-write conflict. Because T3's action came first, it creates a dependency. It means T3 has to come before T1. So on our graph, we draw an arrow and edge from T3 to T1.
On to the next one. At time T4, T2 reads data item Y, and then a little later at time T6, T3 writes to Y. Bingo! Another conflict. This tells us that in any safe equivalent order, T2 must come before T3. So let's add another arrow to our graph, this time from T2 to T3.
And we've found a third one. You're getting the hang of this. At T5, T2 reads Z, and much later, at T10, T1 writes to Z. You know the drill by now. It's a conflict, which means T2 has to happen before T1. Let's draw our last arrow, from T2 to T1. And here it is, the result of our investigation. After combing through that schedule, we've mapped out every single dependency. The arrows clearly show that T2 has to come before T3, and that both T2 and T3 have to come before T1. This is it, our completed conflict graph. Our investigation is done, we've gathered all the evidence, we've built our graph. Now it's time for the moment of truth. Let's deliver the verdict and see what it all actually means.
So, here it is, the big question. Based on this graph we just built, is this messy, interleaved schedule actually safe? Is it conflict serializable? Can we trust the final result?
And you know what? The test is amazingly simple. We just have to look at our graph for one thing and one thing only: a cycle. A cycle would be a loop, right? An arrow from T1 to T2 and another arrow that leads back from T2 to T1. That would mean T1 has to come before T2, but T2 also has to come before T1. That's a complete paradox. It's impossible. If there are no cycles, we're in the clear.
So let's look at our graph one more time. Do you see any loops, any arrows that lead you around in a circle? Nope, they all flow in one general direction. So the verdict is in. Our schedule has no cycle, which means it is conflict serializable. It's safe. Case closed.
So what's the big payoff for all this detective work? Well, a graph without a cycle doesn't just tell us that a schedule is safe. It actually tells us what the safe equivalent one-by-one order is. We can actually unwind the graph to find the hidden sequence. Here's how we do it. It's kind of like a little puzzle. First, we look for a transaction that has no arrows pointing to it. See that? It's T2. That's our starting point, so we can pull it out. Now, with T2 gone, what's the next transaction with no incoming arrows? It's T3, so we pick that one next. And finally, the only one left is T1.
And there you have it. This safe serial order that our complicated schedule is equal to is transaction 2, then transaction 3, then transaction 1. If we had just run the operations in that simple one-by-one order, we would have gotten the exact same final result as our fast interleaved schedule. We got all the performance without sacrificing any of the consistency. Pretty cool, huh? So we solved this particular mystery. But this brings up an even bigger question, doesn't it? What happens if our graph does have a cycle? That signifies a really dangerous situation, basically a data disaster waiting to happen. And that's why real-world databases don't just check for cycles after the fact. They use really clever techniques like locking to prevent these cycles from ever even forming. But that's a whole other mystery for another time.